progress okay on the chat. In the meantime, welcome everyone to episode 56 now of GPU mode. We have Georgii again from the NVIDIA CUDA team here to talk to us about benchmarking. I think Georgii, at this point you are our most common speaker. I think you're the only speaker who's given 3 lectures so far. So it's good to have you back. And yeah, without further ado, Georgii, please take it from here.
Thank you for having me, and for audience, thank you for attending today. I'll be talking and telling you some kernel benchmarking tales today. And first, let's figure out what benchmarking is. So, benchmarking is a tool that is needed to answer one of the most basic questions about your CUDA kernels. First question to ask would be, does your kernel provide correct results? And this set of questions are usually answered by unit tests. And once you answer the correctness questions, you can proceed to the question about the performance. So, how fast is my kernel? And this kind of questions are usually answered by profilers and benchmarks. So, while profilers and benchmarks provide technically correct answers, the journey to discover the answer often resembles a Grimm's fairy tales, and hence the title. This area is deceptively familiar at first glance, but it turns into a nightmare fuel as you keep going. So let's actually try to answer the performance question for device select. To be specific, so imagine you have an application and somewhere in the middle you have call to cup device select if. If you're not familiar with this algorithm, what it does is it takes an input range and an operator as a predicate here on the screen that returns you true for all odd numbers. So if your input is 1, 4, 3, 1 is selected by predicate, so it is getting compacted in the output range in place in the data. 4 is discarded, 3 is compacted, so you have 2 in the output here. Let's say this kernel provides you correct results. Now, our question is it fast or not? And at application level, how do we figure out this? The first thing you should start with is using Insight Systems. Insight Systems is a profiler that gives you a system-wide view of CPU and GPU activities. It will visually represent some asynchronous kernels, memory transfers, etc. So let's try and use this one. When we use Insight System with our kernel, with our application, we see some measurement with NVTX here. Because device select relies on decoupling back that we discussed in details in one of our previous talks, this algorithm consists of 2 kernels actually. First one initializes some tile states per thread block in global memory, and subsequent kernel is using that and actually loads the data. So we can take a look at the NVTX range to discover that this algorithm takes 92 microseconds. So that's kind of easy. But it's not the only tool that is available to answer performance-related questions. NVIDIA also provides you a tool called Insight Compute that gives you a detailed performance view of your kernel. It gives you a source-level correlation with some performance metrics and guided analysis for performance optimizations. So let's give this one a try. We call Insight Compute with our benchmark C2 kernels again, but something is odd here. When we add the duration times for both kernels, we get 114 microseconds, so more than we saw with Insight Systems. Why is this happening? Well, the answer is somewhat on the screen. Here you see that Insight Compute reported the frequency at which GPU is working. So here we see 900 megahertz, but the GPU that I'm using here, it's A6000 Ada. It can boost up to 3 gigahertz. So inside compute locked clocks the base value here, and and that led to poor performance on the algorithm end. So we can actually control this behavior. You can tell inside compute to avoid locking clocks, and this will reduce the elapsed time for our algorithm significantly, almost twice here. But it's still confusing. Like now we see 57 microseconds, while inside systems reported 92. What is going on here? To answer this question, we have to understand what has to happen for us to launch a kernel in the first place. So initially, we have a device code somewhere on, let's say, a disk. We have to load the data into RAM, process it, and put it into global memory on the GPU before we call a kernel. And previously, all the kernels, all the device code was loaded at the application start time. That means if your application has thousands of precompiled kernels, and let's say you're only using a few of them, you have a lot of overhead coming from that startup time. That is why in CUDA Toolkit 12.3 forward, we switch the default to a lazy loading of the device code. This means that the device code will be processed and loaded into global memory upon the first use of a kernel. And this takes significant time that slows down our profiler. You can actually control this behavior and set a CUDA module loading environment variable to eager mode. With that, all the kernels are loaded at the application startup time again, and we don't incorporate the time it takes to load module into our profiler. And this helps. As you can see, inside compute and inside systems now report approximately the same time. There is a minor delta here that is actually caused by the fact that inside compute gives you per kernel results, while the inside systems gives you an actual time span it takes to execute the algorithm consisting of multiple kernels. Between the kernels, you'll see a small delta that is caused by kernel teardown and setup time. And this time is not incorporated inside compute. So it kind of makes sense. Now we can try to shift our perspective a bit. So we, at the application level, when we use an accelerated algorithm, we can ask a question of how fast is this kernel in my specific use case? That means for device select, if say 50% of the data is selected, when the problem size is like 200 million elements, and the type of these elements is, let's say, char. These kind of questions are answered by profilers. But as you develop a kernel, you shift perspective to asking a question of how fast is my kernel across variety of use cases. So you need kind of a unit test for performance of your kernels that covers a wider set of workloads. For device select, how would it perform with, let's say, one selected item on 200 million selected items? What if the data type is double? It's all helping you to reason locally about your kernel as you develop it. So instead of thinking which input to the huge application, let's say which LLM I have to load, that would result in a bit different use case for my device select that I work on it. You can just reason locally about the device select code, thinking about in terms of entropy of the input, percentage of selected output, data types of your input range, etc. So this gives us a clear cut between profilers and benchmarks, because profilers are essentially performance debuggers. They give you a single-shot analysis of specific execution, a deep dive into what is happening now. They also have a much better hardware visibility, while benchmarks are kind of performance unit tests. This can be used in, let's say, performance CI, and these are usually covering a wide range of workloads like input sizes, data types, etc. So let's give it a try and write a benchmark. Now we have to time the device select ourselves. Let's try to do that trivially and just put std_cron around that one, see what happens. And something wrong is happening. You see that we get about 4 microseconds, and this is unrealistically fast. And as you probably guessed, this is caused by the fact that device select is asynchronous as any CUDA kernels. So we are not timing the time it takes to run the algorithm. We're just timing the time it takes to launch these kernels. To fix that, we can wrap our code with CUDA device synchronize. First one we add before timing the begin event, and that prevents timing different asynchronous operations on the same stream. We can also add CUDA device synchronize before the end measurement. This way, we wait for the algorithm to finish before we time the end event. So this helps. We now see more or less realistic 100 microseconds, but it's, again, twice as far from inside systems with eager module loading. Why is this happening? So 100 microseconds is the range we already saw in inside systems when we relied on lazy loading. And this is actually the case here as well. So we haven't set up this variable on purpose because let's say you don't want to set eager mode for the whole benchmark. You're just interested in not having lazy loading for your particular algorithm or kernel. To work around that, we can have a warm-up run. So here we just issue a cap device select if, synchronize to wait for its completion, and then time it again. This helps. Now we see 57 microseconds, but it's kind of faster than what we see with inside systems eager mode. Why is that? So that helped because the first invocation triggered all the loading of the device code into global memory, but it also preheated L2 cache for us. Now, all the data that the algorithm will be reading is already resident in L2 at the time of the second invocation. So it kind of puts the algorithm into an unrealistic scenario. To work around that, we can try to flush L2 cache. So simple way to do that would be just writing a bunch of random data to evict anything that was resident in L2. And that helps. So you see that now we get back to 66 microseconds, which is slower as expected, but still kind of far from inside with the eager mode that takes only 60 microseconds. What is the cause of overhead now? To answer this question, let's take a look at the current benchmarking scheme. What we do is that we register a certain time with chrono now. This gives us T0. Then we launch all the kernels. Then we issue CUDA device synchronize that synchronizes with some time, let's call it TS, in this stream. And then we wait for or record event for end measurement with chrono now that gives us T1. The problem here is that we are interested in getting end measurement as close to the end of the kernel as we can. But CUDA device synchronize is doing more work. It actually waits for GPU to finish work and then synchronizes CPU with that. That obviously takes some time. So what we want to do is we want to get rid of the overhead between TS and T1. How can we do that? We can rely on CUDA events to do that. So if we just record CUDA events, we are not incorporating the time it takes to synchronize with the CPU. So T1 should be much closer to the end of the kernel. In code, this might look something like this. So we still have warm-up run, then we flush all to cat, then we create two events, record the start event, issue our asynchronous kernels, record the end event, synchronize with the event, and get the elapsed time with CUDA event elapsed time call. Okay, that gave us much better results. So now we are closer to Insight with an eager mode. We removed some of the overhead, but we are still kind of far. What is going on? To answer this question, let's take a look at the current scheme again. See how the recording of the begin event is quite far from the start of the kernel on the GPU end. This overhead is caused by the time it takes to launch a kernel on the CPU end. This is called a kernel launch latency, and we are not interested in this time because we are trying to understand how long it takes the work to be done on the GPU end, not how long it takes to launch this work. So how can we bring T0 closer to the kernels? We can kind of trick the system by trying to block the CUDA stream. With that, we can record the start event, launch all of the kernels, and record the end event, and then unblock the stream. If we could do that, we would bring T0 much closer to the kernel start time. So with these changes, if we warm up, flushel to block the stream, recall the events, issue the asynchronous operations, record end events, and unblock the stream, we get very similar time to what Insight Systems is reporting. So this is quite accurate measurements. But it's not exactly full story. There is a second reason for the title of the talk, benchmarking tales. If you benchmark this invocation multiple times, you'll actually get a distribution of measurements, not a single value. It is partially true, like any fairy tale, that 880 microseconds is somewhere in that distribution. But the kernel can take faster to run or slower to run. So the part of fairy tale here is that we can represent the entire distribution with a single value. So that's a good point for a quick recap. At this point, we figured out that profilers are performance debuggers, benchmarks are performance unit tests. We also understood that accurate timing of CUDA kernels requires warm-up runs, L2 flashes, complex use of CUDA streams and events for better, and that ideally better left to special tooling that we'll talk about later. But most importantly, we realize that measurements are noisy, and this leads to a requirement on multiple measurements. If we measure multiple times, we have to ask a few questions. First, can or should we try to reduce the noise we get in the data? And the second question is, how many measurements do we have to perform? So let's start answering the last one. The easy way would be to just issue, 100,000 invocations on the kernel and just compute the average time it takes to run the algorithm. But if we do that, we see completely strange results. So now it takes an order of a millisecond to run the kernel. While previously we were in the time frame of 800 microseconds. So what happened? To figure out the answer, we can try to see what was the frequency of the GPU while we collected these measurements. As we collect measurements, you see how the frequency starts dropping. That is caused by the fact that our select implementation is very efficient at heating up the GPU. As the GPU heats up, it starts dropping frequency that is called a throttling. This throttling has an effect of the execution time for our device select, which results in about 35% difference in elapsed times. So what can we do about that? Is the variance caused only by throttling, or there are other factors? To answer this question, we can try to sort the data by the frequency range. And first thing that it helps us to do is to realize that our device select implementation is in strong inverse linear correlation with GPU frequency. So it kind of makes sense. The slower GPU works, the longer it takes the algorithm to run. But there is second observation that we can make. Within the same frequency range, we have about 2% variation of the runtime for our algorithm. This is caused by the concurrent nature of device select. I selected it for a reason. It has some complex concurrent mechanics inside that you can, if you're not familiar with decoupled lookback, you can take a look at one of our previous talks about that. But the long story short here is that decoupled lookback doesn't have deterministic performance. So we do have to benchmark multiple times to figure out what is the actual representative set of performance states that this algorithm can be in. But there is another takeaway we can see from this plot. The dark greenish color here was observed by feeding the algorithm with uniform distribution and selecting all the elements. If instead of that, we just have, let's say, some constant that is close to zero, and we select this constant in a way that leads to all the same number of elements being written back to memory, all the same code paths are taken in the kernel, you can observe that the elapsed time can drop significantly. So why would that happen? Why would the same code paths lead to different frequency scaling, different execution time? Well, I selected this workload to show that values close to zero means all the bits in these values are zero. And zero means there is no current through the chip. And less current means less heat. So you just can observe different throttling behavior by selecting different workload or input that doesn't affect any code paths in your code. For us, this means that as we work on the benchmarks, it's crucial that we spend some time to prepare some realistic workload instead of just feeding some random artificial constants. But anyways, how can we reduce this variance? Let's say we do have to benchmark uniform distribution because it's more realistic and representative of what application will fit into the device select. Can we reduce this variance somehow on the hardware level? Well, we can try to look at, let's say, max clocks to be as close to the user setup as we can. Let's try to look at 3.1 gigahertz and see what happens. And here you see how we started somewhat higher in frequency range, got some better, faster elapsed times initially, but faster GPU heated up sooner. So we have a small dip in frequency range that overall doesn't really affect the variance of the elapsed times in this 100,000 time invocations of the kernel. I don't know what we expected actually. Like, it doesn't make sense that GPU will maintain 3.1 gigahertz because if it heats up, what should it do? Like burn? We probably don't want that. So it has to scale if you look at max clocks. For us, this means it doesn't help. So what can we do? What else can we do to reduce this variance? Well, obvious choice would be to then look at lower clocks. So not looking at max, but selecting some low value, let's say 2.5 gigahertz, 2.2 gigahertz, and see what happens with the algorithm. Let's try to do that, but use a bit different algorithm this time. Let's try to use device histogram. And this leads to some surprising results again. So let's say I benchmark histogram even on the very same workload, very same problem size, data types, all the values are the same. But I benchmark it at 2.5 gigahertz and then benchmark it at 2.2 gigahertz. On this screen, you see how this affects elapsed times. I presented density of like distribution histogram here that shows for this elapsed times how many measurements we gathered. And you see that at 2.5 gigahertz, we get about 2.7 microseconds. But then as you lower the clocks, it takes algorithm becomes faster. So we have about 6% speed up from lowering clocks, not raising them. And this is somewhat surprising. Like, why is this happening? Well, histogram is atomic heavy algorithm. At some point, we issue a lot of atomics into memory, which causes contention. At higher clocks, it makes sense that we issue these atomics at higher rate. But if we drop this frequency on the GPU end and keep the memory at the same frequency, we issue atomics at lower rate, and this means contention is lower, and this might have positive effect on the performance. What we see in the data on the screen. If you now try to plot the distribution of elapsed times for every frequency of the GPU, you'll see that it behaves something interesting here. At first, it makes sense. It takes less time at higher frequencies, but as you reach a 2.2 gigahertz range, the time to run the algorithm start growing, then drops a bit, and this is somewhat, let's say, nonlinear behavior of elapsed time dependency on the frequency. Okay, what does it mean to us? Can we look at lower clocks or not? Well, it's a good time to ask a question, why are we interested in the accurate measurements in the first place? Or the stable measurements? So usually you're interested in stable measurements when you're trying to compare something. For instance, you might be interested in, has my kernel regressed performance? Or does my change lead to performance improvement or not? But when you have a nonlinear dependency of elapsed time on the frequency, the answer might be surprising. Let's say we have a histogram again, and this time we're interested in a change. We want to change the thread block size from 300 threads to 1000. How will this change affect performance? Well, on the left you see 2.2 gigahertz locked GPU. On the right you can see 2.5 gigahertz locked clocks. On the left you see how this change regressed performance. So going from 300 to 1000 threads regress performance. And it kind of makes sense because we're not issuing enough atomics to create contention on the memory end. So increasing the thread block size just dropped occupancy, so less concurrent thread blocks working with histogram, it's a regression. But at higher clocks, reducing the occupancy helped because we got less atomics issued, but larger thread blocks working on larger privatized histograms, and that noticeably helps. So long story short, if we log at lower values of the GPU clocks, we are risking to observe a change in performance that is not representative of a real setup. Users of your kernel will not log clocks. They're interested in the max performance of the GPU. So if you observe, let's say, a regression here on lower clocks, you avoid applying this change that actually led to significant performance improvement on higher clocks that are more representative for user workloads. But opposite might happen as well. We saw a few times how on lower clocks, you see a performance improvement, but then at higher clock rates, performance just regresses. So it strongly depends on the shape of the dependency, your elapsed time from frequency of your GPU. And for some algorithms, it's not as bad. So adjacent difference is one of the simplest kernels we have in Cub, and it pretty much doesn't depend on the frequency of the GPU, because this algorithm is GPU is memory bound. It has very little compute, so it kind of makes sense. So what kind of takeaways can we make at this point? It's not safe to log clocks at lower rates. It doesn't help to log clocks at higher rates. And we have variance caused by the algorithm itself, so we have to benchmark many times. But we have this problem of excessive throttling caused by the amount of benchmarks that we launch. So what we can do instead is we can try to measure the average frequency of the GPU during our benchmark, and then just discard the measurements that happen during obvious throttling. So here I declare a max frequency that can be queried using CUDA API. You can also get the average frequency, and threshold is user controlled. Let's say I'm telling that 75% of the peak I would consider unrealistic for my application. So I'll just discard these measurements. That would help us get more representative sample for the performance metrics we collect. There is also a tangential question of should I log CPU clocks or not? So because of the blocking stream approach we discussed previously, we are not really incorporating the time it takes to launch a kernel on the CPU end. Therefore, CPU doesn't have a way to impact our measurements right now, and it doesn't help to log clocks. On this screen, you see how I compare locked and unlocked CPU clocks with the measurement scheme we presented previously. And you see there is like little difference in variance. Okay, so we shouldn't lock clocks, but we still have a problem of 100,000 measurements. It's kind of taking too long. For some workloads, it can take like half a day to run. And this is just a single workload. We can actually have many data types, many problem sizes. That was the purpose of the benchmarking. So we're interested in reducing this number of measurements as much as we can. How can we do that? We can try to rephrase this question a bit to have an analogy. Let's say I have a dice, but I don't know how many sides it has. How can I figure out how many times I have to throw this dice to understand the number of sides? To answer this question, we can refer to a Shannon entropy. So Shannon entropy is representing a expected amount of information needed to describe a state of a random variable. On this slide, you see an equation for it. So P of X is a probability of observing event X. For us, event X means side of the dice, like observing 1 or observing 2. In the context of performance measurements, it's a concrete elapsed time we observe from the CUDA events. So let's try to throw the dice once. Let's say we rolled 6. The only event we have is 6, and we observed it once. So the probability of observing 6 is 1, and the standard entropy gives us 0. This makes sense because there is 0 information needed to describe the next random variable. From the data we saw, it will be 6 again, so it's kind of easy. If you roll the dice second time and observe 2, now we have 2 equally likely events. So 1/2 for 6, 1/2 for 2, and the Shannon entropy raised. Now it's giving us 1. So now we have to get more information to describe the next roll. It can be 2 or it can be 6, we don't know. And as you keep rolling, you see that entropy increases with each new or surprising measurement. If we roll 19 times, we finally see the last side. So it was like 6-side dice. We rolled 1. And ideally, if we knew about the actual number of sides on our dice, we would stop here. So after 19 rolls, we would say, that's enough. So you see how entropy started kind of saturating as we roll more and more, because it's getting less and less surprising to see each new measurement. But we don't know actually that we have 6 sides. Maybe there are more. So let's try to roll 47 times. You see how entropy completely stalled. Now it doesn't reach any further. It kind of saturated. We can use this property in our benchmarking to come up with a stopping criterion. Let's go back from the throwing dice to performance measurements. And for the select, try to track the entropy of the sample over time. You can see here the same effect. We get less and less surprising measurements as we keep benchmarking. And we can try to run a linear regression on the window of entropy to see where linear regression indicates a saturation of entropy with a certain confidence region. With that approach, we can stop much earlier. So here we stop at about 800 measurements, which is more than 100 times less than what we previously had, while raising the question, do we actually see all the performance distribution that we observed previously? Well, here I'm presenting a plot of the 100,000 measurements versus 800 measurements we collected with entropy stopping criterion. And as you can see, it's kind of not ideal, but we cover at least the same span of elapsed times as this excessive benchmarking and the same span of frequencies. So we get more or less realistic distribution for the measurements we're trying to make while reducing this measurement as much as we can. But implementing all of that is getting kind of unwieldy. It takes a lot of effort to implement all the blocking stream approaches, all the stopping criterions, warm up, L2 flashes, etc. So it kind of makes sense to abstract all of that out into a framework. And that's exactly what we did. So we came up with NVBench that feels a lot of like Google Benchmark, if you're familiar with this tool. But the difference here is that it supports CUDA natively. So it understands CUDA timers, devices, cache flashes, It is also improving stability of benchmarking a lot with blocking stream, sound stopping criterion that is entropy-based. It also has a lot of utility in powerful parameter sweep frameworks that allows you to explore the workload space easier, and also a convenient, flexible command line interface. So let's take a look at how the benchmark would look like if we used NVBench instead. Benchmark is just a function that takes NVBench state reference, and that you later register with NVBench bench macro. With this, you can also register different access for parameters of your kernel. For once, we're interested in how our select performs for small, large, medium problem sizes. So you can register an access called elements here with 3 values. So the benchmark is going to be invoked 3 times. Inside the benchmark, you can retrieve the current number of elements with state.getIn64. You can have as many of this access as you want, and the NVBench will cover the full Cartesian product of these workloads. Inside the benchmark function, you have a setup stage, which is convenient because sometimes you have to spend time preparing the workload, like generating data with certain distribution or reporting some of the metrics to NVBench. So this place is not going to be timed by NVBench. It is purely a setup that is not incorporated into any of the timings. Inside the state exec is where we hide all the complexity of benchmarking. So this state.exec will perform a warm-up run. It will invoke the kernel multiple times until the stopping criterion is saturated. It will also increase accuracy of the measurements by blocking kernel will try to flush out to throttle detection is in place. So everything we mentioned in this talk is going to be implemented on NVBench end. Inside the kernel launcher you provide to state exec, make sure to launch your kernels on the stream that NVBench provides. And the report of NVBench looks something like this. So you see the workload the benchmark was launched with. So here it's elements. You also see how many samples were gathered during the benchmark. You see the some statistics of GPU time. So here's like 814 microseconds that actually happen to be lower that we observed with inside systems, because inside systems gave you just an outlook for one concrete invocation. But as we figured out, we have to benchmark more to exhaust all the states. So 814 was kind of the average time the algorithm can run. But you can also see the standard relative deviation called noise here. So you know that 2%-ish variance in the elapsed time for this concrete workload is intrinsic to the concurrent nature of the algorithm itself. These benchmark results can be presented with Markdown or JSON formats if you want to make it part of your CI. But there is another column that is of interest, and we haven't discussed. Here you see batched GPU time, which is much higher. What is that? So not all kernels are kind of one-shot use. Some kernels are intended to be used in a hot loop where you have many back-to-back, let's say, matrix multiplications. In this case, you're not interested in getting one algorithm invocation as fast as you can. You're usually interested in the batch of these algorithms to perform fast. This means that sometimes you would tune algorithms differently. In device select, we observe that we have a busy loop with a delay to reduce memory contention. And when we raise this delay, we kind of deteriorate the fast use case, but we improve the use case for when this algorithm is used within the batched segment. Because this algorithm hits GPU less, you throttle less, and overall, on average, this leads to better performance. So if you're interested in this kind of batched measurements, this is the field you should be looking at. But also, the different use case for batched measurements is when your kernel is relying on L2 cache residence. So when you do want to have data left in L2 cache so that subsequent call to the algorithm reuses that, that's another use case when you're interested in multiple runs performing faster rather than a single invocation being fast. But as you use batched measurements, sometimes it's not actually needed for your algorithms. So you can disable that with NVBench exec tag no batch. This will disable batch measurements. If you do need batch measurements, be aware that batch measurements will not flush L2 cache. It will not try to detect throttling. It will give you like actual production close results. Different part that you should be aware of is throughput information. You can report the number of bytes your algorithm is reading and writing with state.global memory reads and at global memory writes. This is needed for speed of flight analysis that we also mentioned in one of our previous talks. So if your algorithm is memory bound and you need speed of flight analysis, you can register logical or like theoretical number of bytes your algorithm should be reading. So for select, let's say if we know the percentage of selected items is 100, we know that we are going to read and write exactly number of elements we feed into the algorithm. So that would be a theoretical lower limit of number of bytes that our algorithm should be reading and writing. When you add this declaration of reads and writes, you'll see new columns in the NVBench output that would indicate what's the achieved throughput of your algorithm. So here it's about 700 gigabytes a second on my GPU, but also the achieved bandwidth utilization. So you see that our algorithm reaches 70% of speed of light. This metric is going to be far from what you see in inside tools because it's a theoretical metric, not an actual number of bytes your algorithm is reading and writing. You can have auxiliary data you read, like global states, tile states that we mentioned for the couple back. These are not inherently needed by the data. It's just an artifact of how the algorithm is implemented. So we don't want to incorporate that into the speed of flight analysis. If you do need this raw DRAM bandwidth, NVBench provides a CAPT integration. So you can actually collect CAPT metrics, hardware metrics with state.collect jump throughput, L1 hit rates, L2 hit rates. And this will report you something very similar to what you'll see in Insight tools. Okay. Here you see the report for L1 hit rate, L2 hit rate, longhand store efficiency, and hardware peak bandwidth. Different part that is worth mentioning is that inside the kernel launcher, you're not allowed to synchronize with the GPU. Because we rely on CUDA stream blocking, if you try to synchronize with the GPU, the blocking kernel will never finish running because we will never reach the place when we unblock the kernel after invoking the kernel launcher. This means that if you have CUDA stream synchronize, event synchronize, CUDA free, like any API that leads to synchronizing behavior, you'll observe a deadlock. To still benchmark these cases, you can add NVBench exec tag sync to indicate that your kernel launcher is going to be synchronizing with the GPU. In this case, we will not block kernels, block streams, which will affect accuracy a bit. So now you'll start incorporating kernel launch overheads into the measurements. So make sure to benchmark larger workloads to reduce the effect of this inaccuracy in the measurements. But also we'll disable throttle detection, so be cautious about that. And at this point, it might make sense to log CPU clocks to reduce the variance a bit. NVBench also can provide you a JSON output for your benchmarks. So let's say here is an example where I made a change in the histogram and used 1,000 or 300 threads in the thread block. With the JSON option, we can dump the measurements into a JSON file and later compare them with NVBench compare script. The result of the comparison you can see on the screen indicates this 4% regression from increase in thread block size on lower clocks. And you can use the scripts as part of your CI as well. Besides that, you can use JSON bin option to actually dump all the sampling data. The sampling data can be later visualized to show the actual distributions of elapsed times for your kernel runs. You'll have one binary file per workload in your benchmark. And this will have all the collected measurements by the module of the ones that were discarded during GPU throttling. If you're interested in that, you can actually read these binary files with just numpy from file. It's just a blob of FP32 values. Okay. Having a benchmark doesn't mean you suddenly don't have to debug your performance of your kernels. To help work with the profiler, we don't need to run the benchmark multiple times. We are just interested in a single run. We don't want the kernel to deadlock as well because inside computer will synchronize kernels. So to make NVBench inside Profiler, you can add a profile option, and that would disable some of the machinery we have on NVBench, but it will allow you to have a deeper insight into hardware metrics. So to get NVBench, the easiest way would be to have a CMake integration with CPM. CPM is a CMake package manager. On the screen, you see how I use CPM to pull NVBench directly from GitHub, and then it's sufficient to link with NVBench main, and your benchmark is ready to be compiled. As you compile your benchmark, make sure to compile release builds. If you compile with -j or debug info, that will disable all the optimizations on the compiler end. So you see like a little performance difference, like 6,000% just from this change. So make sure to benchmark release builds. So I wanted to briefly mention what we have on the roadmap. One of the next things that we actually use extensively on the CUDA core libraries and is data generators. Some of the patterns are quite common for preparing the workloads for your benchmarks. Sometimes you're interested in uniform distribution. Sometimes you're interested in the data with a certain entropy level. Sometimes you need a log normal or uniform distribution of segmented.
Excuse me, Georgii, just before you keep going, I did want to ask you a question on the previous slide.
Yeah, definitely.
Maybe it was a few slides back. Anyway, I'll just ask my question, which was, so at least like within like the Pythonic ecosystem for like micro benchmarking, like people have really like Triton's do bench function. What it does is it basically just clears your L2 cache, and then
Yep.
it uses CUDA graphs to like remove like kernel launch overhead.
Mhm.
And it's been like quite convenient to have like a lot of these best practices available
Mhm.
in something that's like a single Pythonic function you can call.
Yep.
And I was wondering, is this like something you've also been exploring in NVBench?
Yeah, I'll try to briefly touch on that one a bit later. We currently working on a modern version of the kernel launch interface. We considered integrating some of the benchmarking facilities in this one so that with some, let's say, macro, you can enable benchmarking of all of your kernel launches. So we thought about that. We have this on our wish list. But I'll touch on Python a bit sooner as well.
Sounds good. Okay, thank you.
So for generators, there are many patterns that you kind of want to reuse. In many benchmarks, you don't want to cook uniform log normal distributions for, let's say, segmented problems with certain properties like mean and max segment and the total number of elements. So we're considering upstreaming this part from CUDA core library benchmarks to the NVBench upstream. Different part that we heavily rely on in core libraries is tuning infrastructure. On this slide, you see how this looks in code. We declare two comments with ranges, one for, let's say, items per thread that we are going to use. This is going to be a compile time variable. So you see like this CUDA std array can be used with this tune items macro. But also the number of threads per block can vary from 64 up to 1000 threads. And we don't want to choose this manually. When your search space for this meta parameter starts growing, manual work becomes on optimization, on tuning becomes very error prone and tedious. So we automated that and considering upstreaming this functionality into NVBench so that when you just describe the tuning parameters, meta parameter space in your benchmark directly, NVBench would be reused to find the optimal combination of, let's say, thread block size, items per thread, and many other parameters. And besides that, we're also thinking about the, we actually drafted the Python exposure of NVBench. This is helpful when you are trying to compare performance across the language, because you can just produce the same JSON output from Python and C++ and then compare that with usual NVBench compare script. And we're actually considering different interfaces for that. One that you mentioned right now that would just be a single function that is benchmark development. But anyways, that is on our wish list. So for takeaways, profilers, performance debuggers, benchmarks, performance unit tests. You have to use both. And while representing the performance data, you don't want to stick to a single value. It's pretty much impossible. Algorithms take a span of performance states, and you should be aware of this distribution. So you have to embrace the noise in the measurements and rely on statistically sound methods to work with that. Measurements are noisy, and we have to benchmark multiple times. You have to make each measurements accurate while you're doing that, with eliminating lazy loading, with warm-up runs, auto flashes, and streams events logic we discussed previously. For the one of the questions we had before, can or should we try to reduce this noise? Answer is no. You should discard complete throttle, but overall, you have to be as close to the production environment the algorithm will be run and see the whole distribution. And for how many measurements do we need? We can rely on entropy metrics and saturation of the entropy to understand when it's enough. of measurements. And the good news is that NVBench automates all of these hard questions for you. So where to go from here is like TLDR for this talk is anyone benchmarking CUDA kernel should be using NVBench. Work on NVBench is ongoing, so it's all open source. You can reach us on the GitHub or Discord. So file issues, ask for improvements, or report any bugs you can observe. But also I wanted to say that there is a great talk on more of an application level benchmarking you can find on GTC on demand called Measure Right. And with that, I want to finish the talk. Thank you for listening, and I would be glad to answer any questions.
Excellent. Thank you so much, Georgii, as usual. Now, I was joking earlier today, like Georgie's like I think today like our most common like guest speaker at 3 talks. So like I think even Andreas and I are I think around that range. I think 3 or I forget. Anyways, yeah, like Georgie said, like if folks have any questions, please let us know. I guess like Georgie, maybe to start with, like one sort of thing I found kind of interesting about your talk is like you're like let's say people aren't using necessarily standard tools and they're, for example, just like the conventional wisdom we get is you should warm up, but like you're also telling us like, well, if you like warm up too much and you're like running for too long, you're going to run into thermal issues. And so like it becomes like really nuanced to figure out like what is the right, like actually maybe I should sort of elaborate on my question a bit more. So generally, if like let's say you're trying to, for example, compare a set of kernels, like let's say like in our kernel leaderboard, and decide what's the fastest kernel. And if you want the results to come back at a reasonable rate, you ideally want to have as few measurements as possible that give you like some degree of confidence. And then before, like let's say you declare a winner, you want to be like as comprehensive as possible. And so I'm curious, like if you've also explored more of like the sort of like statistical aspects where like you might not want the most accurate measurement, but like, hey, maybe it's accurate enough for the purposes of producing a faster iteration cycle.
Yep, that's a good question, actually. Most of the things you asked have to do with stopping criterion. So this kind of chart. What you can do is that you can configure most of the parameters we have in the stopping criterion. And we have an interface for you to experiment with stopping criterion yourself. So ideally, you would be able to even create your own stopping criterion that just runs something once. We wouldn't recommend that, but it's kind of possible. But let's say with entropy stopping criterion, you can control the parameters of the linear regression that we use. So you can set R square here or the angle of this linear regression. So let's say you can stop after somewhere here, about entropy of 5 or 6 if you want. So you can further reduce this 4 times if you're interested in like rough measurements.
Very cool. Okay.
Okay.
And I guess, do you mind going back to your slides with the Python stuff?
Yeah, definitely.
Where is it? NVBench. Okay, what are the limitations for like the kinds of input functions that NVBench.reg can take?
Current limitation is like in the C++ interface, it should be a function that takes NVBench state. That's the only limitation.
NVBench state, okay.
Yeah,
and
because
what's NVBench state exactly?
So NVBench state is the NVBench variable that will have exec function that will actually perform the benchmarking. So you see how in add to benchmark, I call state.exec and pass a kernel launcher. You can do anything in this code before calling exec. This segment is not going to be timed. You can do anything in the launcher of your kernel. This is, again, completely up to you. You can launch as many kernels. If you need to synchronize, like allocate memory or something, just make sure to provide exec sync tag. And then, again, there are no limitations. But the shape of add to, like its signature, because it's invoked by NVBench, it's kind of fixed.
And then are there restrictions on like what the launcher function can look like? Like, for example, like what I'm envisioning is like if it's a .forward call in a PyTorch program, like could you just pass in state.exec.forward and expect this to work?
I don't know what .forward is. I'm not
Oh,
quite a compiler expert.
I see. No, this is more like sort of like PyTorch stuff, like which is like ultimately the question is, can this be like an arbitrary Python callable that you can pass in, or is there also like, does it need to look like a CUDA launcher function?
Yeah, this interface has two levels of interaction, right? So here, first one is the benchmark itself. Its role is to purely separate setup from the benchmark itself. Like, what is the region you're trying to benchmark versus what is the setup for that region?
Oh, I see.
This one has specific shape. The launcher has a specific shape as well, because it's intended to just issue all the work on the GPU. So it has to accept this launch parameter that is coming from NVBench as well. For you, it's just needed to get a stream. There are some different mechanisms you can do, like discard some of the measurements from within the launcher if you want. Like there's an API to that. But inside launcher, you can do whatever you want. So you can launch any functions as soon as, like, preferably use the stream that is provided in the launch. That's it.
Okay, very interesting. I think then like we might end up exploring like this kind of API for the kernel leaderboard and just see like if we can make like the sort of total runtime of jobs like decrease, but also increase like our confidence, or at least just make sure like, you know, either our measurements become less noisy or like they take less time.
You should definitely get much more sound statistical results from that, because you'll be able to rely on more representative distribution of runtimes. I saw a few times when you just benchmark an algorithm once and it performs faster, but on average it's worse than some other algorithms. So that would be a great idea to integrate that on GPU leaderboard.
Yeah, like I think it's just like give us a good sense of these problems. But okay, so I don't see other questions in chat, but like again, Georgii, thank you so much. Jake as well, thank you for the good answers in chat. I'll reach out to you guys offline. I'd love to work with you together on this.
Awesome. Thank you all. See you.
Thanks, folks.
Bye.
Bye-bye.